Good morning, everyone. I'm Hal Knowles with the DCP Program in Sustainability in the Built Environment. For the benefit of both people and planet, I've dedicated the last 20 years of my life to researching and promoting the more efficient urban use of energy, water, and landscape resources. Our past thinking assumed buildings were simple machines with prescriptive performance predicated on asset specifications such as the type of lighting, water heating, and air conditioning installed. We spotlighted the greenest buildings from the background baseline with formulaic rating systems. Unfortunately, these asset-based models of building performance were often wrong. We forgot that all buildings have both programmers and users. Thus, our present thinking integrates occupant behavior into the equation. Human plus machine turns house into home. Like programming a thermostat, today's operational models box our human nature into a clockwork conception of the original machine, as if robots are the operators. Yet people are chaotic and unpredictable. So how do we model our dwellings if we are the ghosts in the machine? Our future thinking will use nonlinear dynamical models to treat buildings as extensions of their living inhabitants. If home is where the heart is, then I believe the heart of home health hides between its beats. 12 monthly utility bills provide poor performance information. Conversely, advanced electric smart meters annually measure thousands of consumption intervals per building. These pattern pulses serve as a coded cadence of changing conditions, both climatic and communal. To paraphrase Albert Einstein, we cannot solve today's problems with yesterday's thinking. I'm here to suggest that new thinking and tomorrow's solutions await us in other dimensions, fractal dimensions. The Florida coastline and the surface of a tree are fractal shaped. Paradoxically, there's no single measurement to define their length. As our ruler gets ever shorter, their outlines appear ever longer, revealing increasingly more subtle details, though never capturing the full story. These objects and the systems that generate them are too complex to be described by the zero-dimensional points, one-dimensional lines, two-dimensional planes, and three-dimensional solids of Euclidean geometry. Fractals stretch and fold in multi-scale repeating patterns, revealing their essence across the infinite space between these classical dimensions. At our healthiest, our lungs respire, our brains fire, our postures sway, and our hearts beat, with fractal complexities that are neither too simple and regular nor too disordered and irregular. We are adapted for uncertainty, and the fractal forms and functions of our bodies enfold our fitness. Like 3D frames in a universal movie reel, nonlinear time series analyses shed light into the ever-evolving dynamics of these complex systems. As such, the research I'm highlighting today applies the science of chaos and complexity to decode and diagnose the dynamics of building performance and one day possibly even occupant health from electric smart meter data, as if this signal is the heartbeat of the home. Given these conceptual insights, I'd like to briefly summarize two related studies with you. Residential buildings may be described as complex social technological systems expressing component interdependence and chaotic temporal variability. As such, in the first study, we characterize the dynamics of multi-scale relationships of hourly electricity consumption data for 13 occupied Florida houses from calendar year 2013. Statistical approaches included exploratory data analyses with distribution-based descriptive statistics, normality testing, spectral and monofractal analyses, multifractal detrended fluctuation analyses, MFDFA, with surrogate testing, and Ward's minimum variance method for hierarchical agglomerative clustering. Results suggested that the energy use patterns were non-normal, non-linear, and exhibited predominantly anti-persistent fractal complexities. Thus, classical descriptive statistics presuming Gaussian probability density function distributions neither well fit nor well described the data and their interdependent characteristics. Notably, clusters of comparable houses were categorically and statistically different when using descriptors based on normality, such as mean, variance, skewness, and kurtosis, versus those based on fractality, such as Hurst exponent and multifractal spectrum width. We believe MFDFA statistical outputs may serve as novel indicators of residential building dynamics as they better characterize the complex, nonlinear asset and occupancy interactions, and they require no assumptions regarding the PDF distribution shape. The first study offers guidance on data management, transformation, parameterization, and interpretation processes necessary to apply MFDFA to whole house short interval electricity consumption time series data. Multifractal quantification of building performance time series data may be useful on multiple fronts, including detecting and underperforming houses, improving segmentation, targeting, pre and post analyses of energy efficiency interventions, diagnosing building system failure risks, and improving smart grid supply and load balancing in time. we might be able to fuse these building performance insights with the emerging medical field of fractal physiology to study if and how buildings degrade or augment occupant health and wellness. To conclude and reinforce these concepts, mean and variance served us well for a time and will continue to do so when properly applied, but we need new ways of thinking to traverse the growing ecological rift between human civilization and our earthly nature. On its own, my research is probably pretty insignificant, but the fractal method to my madness may hold the key to the next thoughtful stewardship of this earth. In sharing the qualitative power of fractals, MIT mathematician Michael Frame states, a fractal description of an object is a story about
Thank you so much for sharing.
Thank you.